bisector, a perpendicular bisector, did two things. It created two right angles. And what else did it do? The word bisect that long ago. What did that mean? Yeah. So it creates two right angles, and then it split a segment, and it created two congruent segments. So if you look at what a perpendicular bisector looks like, just in a generic sense of a picture. If I take a segment, call it AB. And I'll say that CD is the perpendicular bisector of AB. You guys might want to write this down. I'll be crazy. If I'm looking at something that's a perpendicular bisector, it is a very easy thing for us to write up. What happens here is that you can have any diagram, any picture. If you know that you have what's called a perpendicular bisector, you can do the following. You know that it creates two right angles. You know that it creates two congruent segments. So what you would do is you would make your little right angles and your two segments that are congruent. You all right with that so far? Now, what happens is that if you put any point that's on the perpendicular bisector, so basically if CD is the perpendicular bisector and I put a point on it anywhere, let's just say we'll start at C. If I put that spot there and I draw to the endpoints, what do I create? Correct, but more specifically, what do you create? Well, two right triangles, okay. How about this? Right. Is CD reflexive? Do you have two congruent triangles then? So you get congruent triangles by what? Side angle side. So which means then these two are the same, don't they? Now, what happens here is that you're using properties from congruent triangles, the side angle side, the reflexive property, to show that no matter where you put a point on a perpendicular bisector, I put one here, is it still going to be equidistant to the sides? It will always be equidistant to the sides because that bottom part was cut in half. And you have two congruent right angles. And no matter where you put the point on the actual perpendicular bisector part itself, it's always going to have a reflexive piece getting to the right angle. Bless you. Which means you will always have two congruent triangles via side angle side. Which means you will always have the two congruent legs, which create, like you were saying, an isosceles triangle. Okay. So what happens is, when you have perpendicular bisectors, you get a lot of other information. You get congruent triangles. You get a large isosceles triangle. If you know you have a large isosceles triangle, then you know you've got congruent base angles, and so on and so on and so on. There's a lot of stuff that you can get out of that. So, excuse me, anywhere you place any point that lies on the perpendicular bisector is always, it's up a bit here, equidistant to the endpoints. not segment. That was bisected. Again, it's super easy definition if you think of it in terms of a diagram. Yes, ma'am? It's a super easy definition if you think of it in terms of a diagram and in terms of, just like I was saying, that whole idea of side angle side. Because you get side angle side because you've got your segments at the bottom that were bisected. So you get two congruent parts there. You get the two right angles, which are always congruent. And then anywhere you go up and down on that bisector, or the perpendicular bisector, that point will always be reflexive to itself on that segment, which always, always, always creates side angle side. So no matter where you go on that, if you are on the perpendicular bisector, you are always equidistant to the endpoints. And it means the same thing saying it backwards. Converse. If a point is equidistant to the endpoints of a segment, then it lies on the perpendicular bisector. And so on, and so on, and so on. Okay. And what happens with us here, it's not that we have to do any proofs with any of this, but what we do is that we're going to do a lot of algebra with this. Okay. The other thing that'll happen is as we go along, remember how we did this idea of mid-segments last week? And mid-segments were super easy because the mid-segments connected the what's? Wasn't that long ago. Connected the, it connects the, what are these three things? The midpoints, so the mid-segments connect the midpoints. Okay, remember all that? Which means this was the same, this was the same, that was the same, and so on and so on. Well, you have three mid-segments, same idea with when we're talking about perpendicular bisectors. You can have three perpendicular bisectors as well. And we'll get into the whole idea of where they meet and what happens with all that later on this week. Because there's a point here that does a lot of weird stuff too. But we'll get to that. We're not, this textbook does it different. It introduces you guys all the different segments that can be created, and then we talk about the points of concurrency later. Yeah, I liked it how it was kind of like, oh, and by the way, this is the block. Whatever. So we're going to get a lot of, what happens a lot in chapter 5 is that there's just a lot of vocabulary. And you'll see that if you understand where the vocabulary comes from and how you can draw a quick picture and do a diagram out of something, it becomes pretty easy. But it's mainly, I don't know, half a dozen or so different terms that you learn about. So we go from there. Okay. Not terrible. That, those. Excuse me. Which lets us to do something like this. How do you know it's nice?
Is there a way to know if it's
Reflexive, good. You get reflexive. Now, you'll notice, is BD perpendicular to AC? Yeah, there's a big red square, so they ask that means perpendicular. Is AC bisected? Yeah, because there's two sides. So that means that BD is the what of the triangle? It's the perpendicular bisector. So, is B on the perpendicular bisector? Which makes the segments themselves congruent. Again, it's the same idea that if you mark this up, knowing that you have side angle side. Once you have side angle side, what do you know about all the corresponding parts then? They're also congruent. So you're still using some of the proof-based ideas, but you're mixing it up now more so with the algebra. So you wind up with a very simple and quick equation of 4x equals 6x minus 10. Normally I wouldn't subtract the big guy, but in this case, instead of having to move the 10s back and forth, I'm just going to subtract the 6x. Just remember that you have a negative value here. Negative 2x is negative 10, therefore x is. And you always can double check yourself, make sure you did in fact do that correctly, because what's 4 times 5? Yes, it's 20. And then 6 times 5 is 30, subtract the 10, and you get 1. Or Alright? And that's the idea, guys. What we want to do is know that these should equal each other. If they don't equal each other, you know that you've done goofed and fixed your algebra. Right? It's pretty clear, pretty clear as you go through some of this. Not terrible? Okay, try again. All right, so this, again, works out pretty quick. You know that they have to be equal to each other because QS is the perpendicular bisector. Are we at the point now where we can kind of do 2 steps at once? Subtract the 3n, add the 7. We get 6 is 2n, therefore we get 3. Always double check it. 3 times 3 is 9, subtract 1 and you get 8. 15 minus 7 is also 8, so we know we're okay. Excuse me. Which then you can do another thing. An angle bisector. What did angle bisectors do? It's a tough one. Good luck. They bisect an angle. That was tough. Congratulations. All right. So an angle bisector bisected an angle. It created 2 congruent angles. Okay with that? Again, this was something that we did in chapter 4 when we worked through proofs, and we did all that stuff. So we know that an angle bisector takes an angle, and it creates 2 congruent angles. You okay with that? Now, this is a little bit weirder to kind of visualize what's going on. When we worry about angle bisectors, when we worry about angle bisectors, we know that we create congruent angles. Now, we know that happens. But what if I put a point here? If I put a point there, and let's just start labeling stuff out. We'll call this Z. We'll call this angle. We haven't named it yet, but we know that that point Z, the distance from there to the vertex, we'll call that X. That vertex to Z, no matter where you put that point Z, would it always be the same? Yeah. It would always be the same. So we know that you would always get some sort of reflexive side. Now, when you are on an angle bisector, or before we get there, when you measure distance on something, when you use a tape measure, how do you measure something? Do you measure it where it's squared, or do you measure it on an angle? Squared. And what I mean by that is, you don't measure diagonal. If I want to figure out how far I am to the wall here, I'm not going to measure to the corner. I'm going to measure the shortest distance. The shortest distance between 2 points is always, well, obviously a straight line, but you want to be perpendicular. When you are perpendicular to something, you are always going to run into it at a right angle. And you will always, excuse me, you're always going to be the shortest distance. So if I take from the point on an angle bisector to the side of the angle, the shortest distance between there and the side would always be a perpendicular line. Be okay with that? And if I do the same thing here, it would also be a perpendicular line. Now, what happens was obviously not drawn to scale here. Look what happens. Let's call this W and Y. XZ is the same distance no matter what, isn't it? Therefore, I can say that it's congruent to itself. Do I have two congruent triangles? No. Oh, careful. Nope. It's angle, angle, side. In this case here, you have angle, angle, side. The way that things are written out, you have an angle, angle, then the side. The side is after the two consecutive angles. So by having this angle, angle, side here, that means that this point Z is always equidistant to the edges. Okay? That point Z is always equidistant to the edges of the angle. This one's a little bit weirder, and we'll walk through this again here. So if a point is on an angle bisector, it is perpendicular and equidistant. Is it equa or equid? Equid. Yeah, that just looked weird. It's equidistant to the side. For some reason, it just looked weird. But then again, it's Monday after 5 days off, so there's that. And again, it's the idea that the reason that it works is because of congruent triangles. Like we said when we did proofs and stuff, guys, it's not that you have to go through life knowing how to do a proof in every case, but knowing how things have correspondence to each other allows you to be able to do other things. And that's kind of why we do all that stuff. Okay. Now, again, what happens here when you have an angle bisector, it's kind of a tough one to draw. Anytime you have an angle, if you bisect it, we know that happens. And anywhere I put a point on the angle bisector, there has to be some sort of a way to create. There has to be some sort of a way to draw so that it is perpendicular to that side. Okay? Being able to see that you can get a right angle here. When you draw to get a right angle, and you draw to get a right angle here, you know that these two spots have to be the same distance. And that's why you get angle, angle, side. And that's how it works. Thanks, sir. All right? It's a weird one to look at, but again, it's the same basic principle. If you lie on the angle bisector, then you're always going to be equidistant sides. Okay? Which again is going to be able to afford us to be able to figure out angle measures here and there, lots of little things, but it mainly works out to be some pretty straightforward. For example, excuse me. Both kids started getting that halfway through the week too. Yeah. Now, do we know if those guys are on the angle bisector? Yes, the answer is yes, because you have an angle at N that was bisected, and from R to P and R to M, they're both perpendicular, which means you have to be able to do angle, angle, side, because of the reflection, which means you can set those two segments equal to each other. And lo and behold, the algebra is pretty easy. As it does. Subtract the 2x over, and x is 5, which means, what's 7 times 5? 35. What is 2 times 5 plus 25? Hey, are those the same? Good. Then you math them correctly. Yeah, like I said, the first couple as we go through, it's not going to be all that terrible. And just like we talked about earlier, when you have angle bisectors, anytime that you have a triangle, you could have up to 3 angle bisectors as well. And you'll have all these weird things that the points go through. There's all these different rules of why all of this occurs. But we'll get to all that fun stuff later on. Okay. Was the angle bisectors the 1/3 truth there? I thought it was, wasn't it? The insect. I don't remember. I think that's the incenter because those 3 segments, because that gets the circle and that's what makes them all. Starting to think I don't like that. Yeah, I probably should have. I like what he did. You're showing what he was doing for a while. He did all the vocabulary. And went all through that. Probably should have that. I probably should have done that. It is always. It is. Let's try another one. Go away.
No, I'll say that. Thank you.
Yeah, did you get your homework? You didn't get your homework. I'll see you later. Again, we have 4x and 9, 6. 6x is 3. Subtract the 4x, subtract the 3. Then we get 3 again. Okay. Always double check your answers, just make sure you didn't screw anything up. Let's see, 6 times 3 is 18. 18 and 3 is 21. And 12 and 9 is also. What's that? Yeah, don't do that. It's usually not good, right? I don't agree with it very often, but I agree. I know, I'm just messing. In case you didn't figure that out. Oh. I didn't want to hurt your feelings. You'll be okay. You don't have feelings, you're a sideboard. Yeah. Now, I want to show you guys what happens. Whoa, sorry. I didn't realize how loud that was. As we get into this more, you're going to start to see other weird-looking diagrams. Like I had stated earlier, you can have multiple perpendicular bisectors within a triangle. Now, all the perpendicular bisectors in this case are drawn up with dotted lines. OQ, OR, OS. Those guys are perpendicular bisectors. Now, what happens here is by giving you guys a little bit of information, you know that you can do that, right? There's a lot going on, and that's kind of what I wanted to get at here. So take a second and draw this up best you can. I know it's going to look awful. I know. It's okay. And it's okay. Because you're right. As we get along further and further and further, we're going to get crappier looking diagrams along the way. It's just one of those things that happens. The reason why I wanted to show you something like this is because, yes, it looks bad. But if you know that in the directions it said that all the points, all 3 perpendicular bisectors met at point O. So that tells you that you have perpendicular bisectors OQ, OR, and OS. That's just from the vocabulary, just from the information they gave us right up front. Now, all I did after I said that we had that perpendicular bisector is I drew in the right angles and I put tick marks on the segments. Are you okay with that? And believe it or not, there's enough information here that you can find every single segment in that triangle. Okay? There's enough information here to be able to do all that. And that's the idea. As we go along further, yes, you get the side angle sides for the congruent triangles. You get 3 different sets of congruent triangles. You don't have all 3 of them congruent to each other. That would only occur if it was an equilateral triangle. But in this case, since it's not, you'll have 3 different sets of congruent triangles. Okay? So if I'm looking at it, if MQ is 20, what's QN? 20, because it's a perpendicular bisector, which means these two have to be the same. Well, if NR is 26, what's RP? 26. If MS is 22, what's SP? 22, okay? So far, so good? Now, going back into this then is NO, excuse me, is point O on a perpendicular bisector? Is that on a perpendicular bisector? Yeah. Yeah. Because, remember I said that O is where all the perpendicular bisectors meet? So that means that this segment here has to be the same as that segment there, isn't it? Which makes MO how much? 6.8. Which means that this much is 26.8, how much is this point? 26.8. Uh-huh. Now, take a look at what else you can do. How do you find the missing side length in a right triangle knowing that you have two other sides? No, they don't have to equal. They could equal each other, but not necessarily. What's that big giant theorem in geometry? Pythagorean theorem. Now again, this is one of those things that they continually bring back that they know that you have seen at some point in your lives, but yet they haven't officially redefined it yet in this class. So Pythagorean theorem says a squared plus b squared is c squared, where c is always the hypotenuse. It will always be the longest length. So what you wind up with then is 20 squared plus something squared is 26.8 squared. Well, you guys have calculators, right? Okay. So if I type my calculator and I put in 26.8 squared, subtract 20 squared, I get 318.24. So b squared equals 318. How do I undo squaring? Square root. Remember how to take a square root in this calculator? It's second square root of your answer, and you get 17.84. And that makes this side 17.84. Which means you can do that again for this triangle here and get this part. Do it again for this triangle here and get this part. Okay. So let's try that. We have a 22 squared plus something squared is our 26.8. And then we have a 26 squared plus something squared is 26.8 squared. So take a second with your calculators and figure out what those other two side lengths are. We're going to figure out what OS is and what OR is. Okay? I'll show you again, when you're typing things in the calculator, there's a way that you can take a square root of an answer. Right? And it's going to be very important that you understand sequencing for how to put things into a calculator, especially as we go forward and we start getting into like trig stuff. Because there's a lot of stuff that you don't need to write down that your calculator will allow you to do. So get your calculators out, guys. I mean, if you have a calculator, now's the time to have it in front of you so that way you know how to do this correctly, because if you don't, then you're going to screw it up. Hate to say it, but it's a math class, you kind of need to have one. Remember, when you're doing this, let's see if this will fit. We had, I believe, 26.8. We had 26.8 squared. We have to subtract out, was it 22 squared, I believe? All right. So 26.8 squared and subtract out 22 squared. You just type in your calculator just like that and press enter. Okay. Now it's in your calculator you have that next answer. All you have to do from here then is take the square root of it, which means you hit second square root of your answer. This answer button is the bottom right corner. You hit second, and that's the negative button. And that will automatically enter in what the last answer you got and put it with. Apparently it says. Oh, did I bump it? I see. So yeah, this is sensitive if you get too close, and sometimes it bumps it. So I hit second square root of my answer, and there's my other sideline. And whenever I round, and I want you guys to get in the habit of this, we're always rounding to 2 digits. So you get, in this case, it would be 15.30, and you can just write 15.30. Okay. Now, whether or not you have the multi-view calculator or the other types of the graphing ones, you still, that answer button is still that bottom right-hand corner. Okay, and it still shows up the same way. So that gets you the one segment. 15. And then the last one was 26, 8, and 26. Square root of that. And I get, how do you round out 6.499 to 2 decimal places? What would it be? 6.5. And as you guys were mentioning, as you get into these bigger diagram pictures, there's just so much more going on, but yet it's not that it's going to be horribly difficult to use. Okay? Let me give you a handful of these to start up with. Yeah, let's get those things started out. We'll go through a little bit more of this tomorrow. We'll do a couple of the larger, big picture stuff tomorrow. These are pretty straightforward, but I'll have more of those bigger ones for you tomorrow. Okay?